Back. So the objective of this week was to create a object detection in the video in a YOLO style. So basically I was given this research paper. I have to go through this research paper, understand what it says. And I was given a set of data. So the data looks something like this. Yep. So which is basically a data frame that has the X and Y coordinates of an image. So, and the image in my case is football players playing in the team, and I was given their coordinates and the orientation and the radius, but for sake of simplicity, I converted everything into squares instead of circles. But yeah, all I was given was some pictures and their data, and I need to use this research paper to build a YOLO-like architecture that does an object detection. So that's all I have to do. So let's try to understand the whole process in big picture. So what I'm trying to achieve here is I'm given some data like this. I have some labels and I have some images. So I need to do a label preparation for this task, which is basically converting all the data that can be compared with the network's prediction. So I need to pre-process the image and I need to send it to the neural network. And the neural network should be in a form of YOLO-V1's architecture, which is basically copied from Google. So, and with the pre-trained weights. So the label preparation looks something like this. Let's say if I divide my image by 3x3 grid or 7x7 grid, the labels will look something like that. For the first grade, I don't have any information at all. But for the consecutive grades, there are players and I'm going to put their coordinates and a confidence score, whether the player is present or not. Yeah, which is basically this one. And the one-hot encoding of the classes. So we have 3 classes. So the output will look something in a format of 7x7 fashion because I have divided the image into 7x7 grid. And I have 5 information, 5 coordinate points plus the confidence score. I have 5 data points for each image, and I have one-hot encoding, which is basically the labels for each image. And the output that I'm expecting from the architecture looks something like this. So because I'm trying to find 2 bounding boxes per grid, so I have 2 coordinate values. Basically, it's 7x7 grid with 2 coordinate values plus 3 one-hot encoding values. So basically, I need to do some mathematics here. Basically, I need to find an IOU score intersection over union for both these bounding boxes and to choose which bounding boxes fits perfectly compared to the other one. And I need to reduce this output to 7x7 by 8, the same fashion as the labels we have. And then basically we need to send in this information into a loss function. So in our case, we will be calculating 3 losses. So it would be 1 for the encoding, 1 for the confidence if the object is present or not. And if so, where is the object present? So the location of an object. So we need to calculate 3 losses for this. And then we need to back propagate to train the model with new loss with the intention to reduce the loss. So that's the intention, and that's what I'm trying to achieve in a big picture. So let's see how it worked out. So yeah, for ease of conversation and for ease of visualization, I converted all my data in the radius orientation form to square form. So because it's very easy for me to relate to a lot of the articles that has been written regarding YOLO-V1 architecture. And it took a lot of time for me to understand the whole picture. But once I have the whole picture, it took only 1.5 days to really code it. So I had few attempts. Let's see what it looks like. So I used a really big architecture with no normalization of the inputs. And if you see the output, for the second image, I'm not getting any loss for the non-object loss because there are objects in every single grid because I've been using a 3x3 grid because I was practicing. So what I did is I tried to do a few things. I tried to reduce the complexity of the structure and I did some batch normalization and I normalized the input as well. And the loss of NaN values still persisted. So I have no idea what to do at this case. And then I realized that since I have a 3x3 grid and every image has some kind of information, some kind of an object or a player in that, I'm continuously getting NaN values for the masked input. So basically I have to print out all the inputs in the architecture and I have to see step by step why it is happening. So once I understood this is the issue, so I increased the grid size, adding more grids. And if you see, the problem automatically disappeared. I'm getting some loss for the non-object loss. So I'm able to calculate the loss now. So what I did is increase the bit size with more data and my model was working perfectly fine and the loss looks a bit satisfying. And I try to visualize this with the predictions. So once we, in the inference part, we send in the picture, this is the output that we get. This is for one single row, and every row represents a grid. And we have something called confidence score, which is basically the fifth element. So this element kind of tells us if there is an object at all in the grid. So I can use this as a threshold to show or display what all images, what all grids has some objects, and if there is an object of certain confidence score, then display it. Yep. So this was my initial output. So if you see, I have given a threshold of 0.5, and it has detected some boxes, but since I'm not very good with visualization tools yet, so it kind of printed everything on the left corner. So I tried to enhance it with a higher threshold, and if you see, the number of boxes has gone down because there are not very many grids with a confidence score of more than 30%. So they were like only 2 or 3 grids. But the problem here is like everything is kind of squeezed to the leftmost corner. So I played around for like 6 or 7 hours trying to come up with this, and it's not really satisfying. It's not actually detecting any players, but with 26 hours of time, this is all I could do. So let's see what I have achieved in the code itself. Yep, so I was given a data set something like this, which has basically X and Y coordinates, which is the center points, and the radius and the orientation which the player is looking at. And since most of the documents it's available in the internet are for squares, so I converted this data into X and Y coordinates with height and their classes. So it was easy for me to visualize then. So my first visualization looked something crazy because initial X and Y coordinates were the center points. So I need to adjust those points to have a perfect squares. So once I adjusted, it looks something like this. And then it's ready for pre-processing. So the pre-processed data looks something like this. So I converted into, yeah, for 3 images. So wait, so what is this 3 refers to? Okay, it refers to the grid size. No, sorry, it's actually the image, number of images. So I have 3 images. Each image has been changed into 448 by 448 pixels and of 3 color channels. And I have the same 3 images with 3 by 3 grids, and each grid has 8 information. So the 8 information looks something like this. The first 5 values refers to the coordinates and the confidence score, and the one-hot encoding followed. So, yep, I applied the normalizations. So this is a visualization after squeezing the images, and I'm trying to visualize the boxes, and it kind of looks perfectly fine to me. Good to proceed forward. And basically, this is all the values of the images that has been normalized between 0s and 1s. I'm trying to visualize it again. So, yep, I have created a batch, and each batch has 3. Each batch has like 4 images. Yes. And this is my architecture. This was my first try. If you see, I chose a bigger architecture, as in the case of YOLO-V1, and I haven't applied any normalization for any convolution layers. So as you can imagine, the result was disastrous. And yeah, this is my model itself. These were my hyperparameters. And yeah, I was not getting any answers for the no object loss. Went like this. And I tried with a smaller architecture with batch normalizations added for every convolutions. You can see it's literally half the size. And yep, with the same parameters, the loss was not changed. And this was the 3rd attempt. The model was kept same, but I have increased the grid size. If you see here, the grid size has been changed to 7 from 3 by 3. And basically, I was calculating all this loss: coordinate loss, object loss, no object loss, and what is the class loss. And yeah, the loss seems to be disappeared. The NaN values seem to be disappeared. And I started to have some loss, which looks pretty much satisfying to me. So I kind of increased the batch size and the number of inputs that I have given, and the loss kind of looks good. And these are my predictions. So I'm trying to save the model and to create a predictions out of it, and I'm trying to visualize what goes on every single step. And yep, with a threshold of 0.3, 30%, it looks something like this. And I've been breaking my head around this part for at least 6 hours with my friend, but unfortunately we couldn't come up with the perfect predictions, though I do have some prediction values, but somehow I wasn't able to plot it. It was simple for the other team members, but for me this part was quite complex. The rest was quite easy for me, and it was a bit of a realization for me that I need to spend a lot of time on visualizing the data. And yeah, these were some few attempts, but nothing worked in visualization. So the objective of this task was to create a YOLO-V1 model. So am I 100% confident enough to create a YOLO-V1 model? No, not really. But I'm pretty confident that what goes behind every single step in the YOLO-V1. So we worked for 4 days straight, non-stop, from 9 a.m. till, I don't know, 1 a.m. in the morning for the next day or something. So it kind of gave me a confidence, even though there are some topics that I'm completely unaware. I can go into internet and search for some information and to come up with a model that is working. And basically what I learned is I need to figure out the 1,000 ways that the model won't work. And probably the next time I try, I would be able to understand what are the ways that won't work. And then I would come up with the answer. So that was a big learning from this week. And this week was very intuitive, challenging. And yeah, I did a lot of research on the internet than usual. And it was a bit satisfying, to be honest, even though it's not 100% success, but I was able to come close to the success. So that's a big achievement for me. Thank you.